computer. Yeah. Okay, here. Start sharing the screen here and okay, so we are writing here. We are going to continue covering special relativity, and Wednesday there will be exam number 3. Labs 3, 4, 5, and 6, chapters 22 through 26. Last one we did was 8. I studied lab 8. I studied on correct lab 7. And we leave 7 and 8 for the final, and hopefully lab 9 as well. And here you go. Semester is almost over, right? We still have next week. It's gonna be last week of classes, and then afterwards we're gonna have a holiday and the final exam. Okay. The material. Let's take a look here at this material. What we covered last time in relativity was time dilation, the phenomenon of time dilation. Okay, and there are other phenomena, but there are other relativistic phenomena. So here go. What I want to tell you, there is a very good set of videos. This is an old video, but it's still very good, and you can find it in the YouTube. And this video, they have a very good explanation for relativity. And those are the episodes of 42, episodes 42, 43, and 44 of the mechanical universe. I'm gonna play some of those videos here so you can have a better idea of time dilation and how clocks work in different referentials. Okay, and see, let's talk here about what we got from relativity so far, right? Surprising results from relativity. One, speed of the light is the same in any inertial referential, whether the referential is moving, whether the referential is at rest with respect to the light source, moving towards it, moving towards or away from it, comma, the speed of the light that is measured in these 3 different referentials will be the same, 300,000 kilometers per second. This is one of the postulates of relativity. Okay. Whether the referential is at rest with respect to the light source, moving towards or away from it, the speed of the light that's measured in these 3 different referentials will always be the same. I'm going to emphasize here, will always be the same. This is one of the postulates of relativity. And the other one the other surprising result that we got is that time measured. Consider here, I'm gonna put like that. Consider two identical clocks. Okay. One at rest with respect to you, with respect to you, and the other moving at constant speed. Constant speed. Okay. One at rest with respect to you. I'm going to put it here, referential A. And the other moving at constant speed, referential B. Okay. The clock at rest we call clock C. The clock moving with respect to you is clock C prime. Okay. So we can differentiate those two clocks. They're identical, but they are different, right? Because they are different referentials. Okay. At rest, the clock at rest with respect to you. With respect to you is clock C. Right? Is clock C. The clock moving with respect to you in referential B. In referential B is clock C prime. Okay. So the surprising result is that, using the postulate, the above postulate of relativity, the above postulate of relativity, we find that T of C prime with respect to A is going to be greater than T of C prime with respect to B. Okay, so here we go. Let's put that out. And there is a very nice video on the mechanical universe that illustrates that in a cartoonish fashion, okay, like that, which was exactly what we got before, right? So I just used a different notation in the previous, here we go, in the previous one. I put C instead of C prime, okay? Okay, this means that an observer C in A, C, the clock B running slower compared to his own clock C prime, right? Let's put it. Let's see if I. You want to take a period? Yeah. So I changed the notation. That's what I did here. I changed the notation now. Okay. And another important result is that, you know what? Let's keep consider two identical clock, one at rest with respect to you and the other moving at constant speed. Let's the clock at rest with respect to you. Let's put C prime here. So we can, and the clock moving with respect to you in referential B. The clock at rest with respect to you in referential A. is clock C prime. The clock moving with respect to you in referential B. Keep it consistent what we did before, right? Using the above postulate of relativity, okay? Here you go. So now the clock that's moving with respect to you is the clock C, okay? Just keep it consistent what we did there. And okay, another important result is that events that are simultaneous in one referential is not simultaneous in another referential. However, keep in mind that in order for something like that to be measurable, okay? One referential must be traveling at relativistic speeds, okay? If the speed is very low, you're not going to notice that. And we can see that from examples. There you go. I have an example here for you. Okay, so here you go. Example 1. Huh? You see a clock moving past you at a speed of 0.1 c, 1/10 of the speed of the light, 10% of the speed of the light. If your clock that is at rest with respect to you measures a period of 1 second, how many seconds would the other clock indicate? Okay? How many seconds would the other clock indicate? 1 second in your clock would be what? How many seconds in the other clock, right? So in other words, 1 second in your clock that is at, let's see, you see a clock moving past you with a, if your clock has a period, let's say, has a period, okay? If your clock is at rest with respect to you, has a period, better like that, has a period of 1 second, okay? The period of 1 second is the bounce between the two mirrors, right? Is 1 second. How many seconds would you measure for the period of the other clock? Okay, that's how you always have to measure that with respect to your own clock, your other clock. 1 second in your clock indicates how many seconds in the other. Indicate how many seconds in the other. Okay. Okay, so here you go. 1 second is the proper time. The proper time. Is the proper time. And we can go back to our equation that we had before. Okay, here's the gamma factor. Let's see. Here's the equation. you see a clock C moving past you with a speed of a tenth of a second. Consider, even better, consider two clocks. Huh? A clock C that's moving with respect to you, at 0.1 C, right? At the end of the speed of the light. And your own clock C prime that is at rest with respect to you, right? Better this way. If the period of your clock, if your clock has a period of 1 second, if your clock has a period of 1 second, how many seconds would you measure for the period? If your clock C prime, right, has a period of 1 second, how many seconds would you measure for the period of the other clock C? Huh? In other words, 1 second in your clock indicates, in other words, indicates how many seconds in the other. Okay. Okay. So 1 second is proper time. Okay. And there's a kind of a difficult way of really grasping this idea in relativity. Okay, but very important. I'm going to tell you. Okay, you know, proper time is that time measured by a clock that's at rest with respect to you. Okay, clock C is at rest with respect to an observer in referential B. So this time would be considered proper time, would be 1 second. By the same token, okay, the clock C prime is at rest with respect to an observer in referential A. So this is also proper time. And it's going to be equal to 1 second. Make sense? Okay. That's an idea that's kind of difficult to picture, you know, to understand, because it's not obvious. It's completely out of the box. Okay. A clock that is in your referential, that's at rest with respect to your referential, has a period of 1 second. And the other clock that's at rest with respect to the other reference is also proper time. So it has to have a period of 1 second. Okay? That's the key information that you need to come up to solve this problem right in here. And now that we have that, we can proceed with solving this problem. Okay, so here you go. I'm going to put 1 second here at the top. Here is going to be 0.1 C. Don't forget that we have to have a parenthesis here. And this one, it has to be squared. And we go ahead and solve that. Okay, here we're going to have, when we square 0.1, we get 0.01. When we square C, we get C squared, right? And now we will be able to solve this equation numerically. Okay, C cancels out with C. What we end up having here is just going to be 0.01. Okay, which is 0.99. Well, if you do the math, you find out that the period that you measure for the other clock with your own clock is going to be a little bit longer, 0.005 seconds, okay? This is the time, this is the time, this is the period of clock C when measured with clock C prime, right? So the idea, the illustration would be something like that. Let me show you here. Okay, here you go. That's what you should look at. The red clock is the one that's moving. The black clock is the one that's at rest with respect to us, okay? In order to measure the period of this clock, you have to have another clock of your own, okay? So when you measure the period of this clock, you're going to see that the period takes longer. It's moving, this clock is ticking more slowly, okay? And this period gets longer and longer as the speed of the other referential increases. Okay, so you can do example 2. Consider 2 clocks, a clock C that's moving with respect to you, and then we're going to do now a little bit faster, half the speed of the light. And your own clock that's at rest with respect to you. If your clock C prime has a period of 1 second, how many seconds would you measure for the period of the other clock? In other words, 1 second is your clock, 1 second in your clock indicates how many seconds in the other. Okay, so just like before, you know, the period of your own clock is going to be 1 second. The period of the other clock measured with respect to referential B is going to be 1 second as well. In both cases, we have proper time, okay? In both cases, in both the above cases, we have proper time. Then we have to calculate what? We have to calculate the period of this clock C with respect to referential A. And we already have the formula. Okay, let's not forget this is proper time. You know, in your book, remember, in your book, TCA is referred as delta T, and TCB is referred as delta T naught. Delta T naught, the naught for proper time. I prefer this notation because it has more information and it specifically addresses which clock we are referring to. Okay, and now it's the same thing as before, right? But instead of 0.1, we are going to have 0.5 here. And 0.5 squared becomes 0.25. Here is 0.25. Here is going to be 0.75. And when you do the math, what did you get? You get 1.155. Is 15% longer. The period that you measure for clock C is 15% longer than the period that you measure for your own clock. Okay. So those are very good examples. And there is another interesting phenomenon that is the events that are simultaneous in one referential is not simultaneous in another referential. And this one's going to be nicely illustrated by episode number 42 of the Mechanical Universe in a cartoonish fashion. Okay, I'm going to play that for you. I have the link right here, episode 42. Okay, so I'm not going to play everything. I'm just going to play what I believe to be pertinent to this lecture. Yeah, here you go. Right here. Play it.
Still observe light moving at 300,000 kilometers per second. How could that be? Consider two observers in relative motion. In this case,
okay, it looks silly, okay, but it's very powerful what you're going to see here. It's a cartoon, but it explains very well the idea of proper time in two different referentials, right? And then he has one character here is Einstein. One observer is going to be Einstein, and the other observer is going to be Lorentz.
Albert and Henry.
There you go.
Just for the sake of argument.
In this very moment, what he's illustrating, the proper referential or in the proper time is that one of Einstein. We are at rest with respect to Einstein, whereas Lorentz is moving with respect to this speed, 40% the speed of the light. Okay, there you go.
At the exact place and time they pass each other, they observe a flash of light.
Here you go, flash of light. And now don't forget, the flash of light is moving at the speed of the light. What you see right here is in slow motion, right? It's in slow motion. And because Einstein sees this flash of light moving at the speed of the light, 300,000 kilometers per second, he's going to see this flash of light moving like a sphere, behaving like a sphere centered at where Einstein is located. Okay.
The sphere of light expands outward from that point.
But according to relativity, the speed of the light with respect to this referential must be 300,000 kilometers per second as well. And now what's happening here? What's happening here is that he transported us to Henry's referential. To Henry's referential. Now the proper referential and the proper time is going to be Henry's, okay? That's what he's doing right now. He's transporting us to referential B.
Since each measures the speed of light relative to himself.
Do you see now that Einstein is moving with respect to us, right?
Each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places
back to Einstein's referential
both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light.
Here you go, that's back to Einstein's referential. And now they're going to find out whether those events here are going to be simultaneous or not, right? According to Einstein.
Arriving simultaneously. He believes the light strikes Henry's detectors at two different times.
You see what happened? Einstein observed two simultaneous events here in his own referential, but in the referential of Henry, the events are not simultaneous. Okay? And then what happens in Henry's referential? Here you go. Don't forget, now we are in Henry's referential. We are transported to Henry's referential. Yeah, according to our referential, Henry's at rest and Einstein's is moving.
Henry sees the same thing in reverse.
There you go.
They agree on the speed of light, but they disagree on whether events happen simultaneously
Or not.
or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion.
Okay, so that's the one idea that was very difficult for scientists to believe. An event in one referential, that is an event that's simultaneous in one referential, is not necessarily simultaneous in another referential. How is it possible, right? But that has to do with the constants of the speed of the light. And that was exactly what I wrote here, right? Let's get back here. Events that are simultaneous in one referential are not, and let's put just an event, let's put the singular that is simultaneous in one referential is not simultaneous in another referential. That's a surprising result. This is consequence. This is consequence of the speed of the light postulate. And all those weird things happening in relativity. Okay, and I'm going to do even better. Oh, here you go, those three here. What I'm gonna do here, instead of making 1, 2, 3, I'm gonna make 1A, 1B, because those two are consequences of this one here. This is a postulate, and what we see here is a corollary, two different corollaries. And there are more, okay? There are more. Let's go back to our, here. No. One more student coming. Where is it? Must be here. Okay, that's here. Okay.
However, as profound as this was, the French mathematician Henri Poincaré objected to the limited nature of Lorentz's explanation. What was needed, he said, was a new fundamental law of physics, the principle of relativity, according to which the laws of physical phenomena should be the same, whether for an observer fixed or for an observer carried along in a uniform movement of translation. In other words, as Galileo had suggested, one state of uniform motion is as good as any other. After all, this idea was the basis of Galileo's reasoning and the law of inertia almost 300 years earlier. But Poincaré was suggesting that the idea of Galilean relativity should be generalized to include all physical phenomena, including light. For example, an observer could not determine whether he was in motion by measuring the speed of light, since that speed is the same for all observers. And that meant age-old notions about time and space had to change. And though Poincaré himself shied away from examining the consequences, Lorentz developed the equations needed to show precisely how much rulers would have to contract and clocks would have to slow down when they were in motion.
Here you go.
The essence.
Now is the light clock, right? Here you go. It's two mirrors and one photon bouncing back and forth. The period of the photon is the round trip between one mirror and the other, right? That's the period of the clock.
Of his reasoning can be seen with the aid of the simplest possible clock. two mirrors a fixed distance apart.
Here you go, the light clock again. And now we jumped into Henry's referential, because Henry is at rest with respect to us. And we are moving with respect to this referential here, right? That we can see this, the lines
with the light
moving.
beam bouncing back and forth between them. Each bounce of the beam is a tick or a tock of the timepiece. To Henry, his clock is stationary and altogether ordinary. But for Albert, that clock is moving. And between tick and tock, he sees the light beam trace a diagonal path, which means it's traveling a longer distance. But the speed of light is the same for all observers. So the light must take a longer time to travel the longer distance. Therefore, Albert believes the moving clock runs slow. But how slow?
Relativity of time is derived from the right triangle formed by the distances traveled. The Pythagorean theorem shows that the path of the moving light is longer than the distance between mirrors. By the factor 1 over the square root of 1 minus b squared over c squared. This factor occurs so often in relativity that it is given its own symbol, the Greek letter gamma.
In this case, the proper time here is delta t prime, okay? In this case, the proper time is delta t prime. Did you notice that this clock is running slower? The period is longer, right?
So to an observer at rest, a moving light clock seems to be running too slow by the factor gamma. A ruler or anything.
There's another important consequence of the postulates of relativity. You see objects contracted. We have time dilation and length contraction.
Everything else in motion also seems contracted by that same factor, and it's called the Fitzgerald contraction.
Length contraction or the Fitzgerald
much
contraction?
less than the speed of light. Gamma isn't very large. For example, the Earth, in its headlong dash around the sun, is shortened by no more than the length of one blade of grass. As for speed on the Earth, while Lorentz was busy developing his theory, the steam locomotive barrier of 100 miles per hour was broken. At that speed, the entire train is shortened by less than the width of one atom of the paint on its engine. And Lorentz himself didn't move slow. He was the international physicist. Young physicists from around the world attended his lectures at the University of Leiden in the Netherlands, where he'd been a professor for a quarter of a century. Among those who came to Leiden was Albert Einstein.
Einstein was here. This one is Marie Curie. She won 2 Nobel Prizes. And Lorentz.
Over the years, Lorentz would have an enormous professional and personal influence on Einstein. Just before his death, Einstein said, "I have admired and loved Lorentz perhaps more than anyone else I have ever known." But it was Lorentz's work as a theoretical physicist that went beyond his privileged circle of friends and traveled freely through time and space. Knowing he was on the right track, Lorentz pursued the consequences as far as he could. If moving things appear shorter and moving clocks run slower, then how can two people moving in relation to each other, agree on a consistent description of where and when some event happened. To answer that, what's needed is a set of equations to replace the old Galilean transformations. These equations weren't hard to find.
Okay, we can stop here for now. And on this video, what I want you to see was those cartoon, okay? But very soon we are going to go back to this video. And let's talk about length contraction. Here already mentioned length contraction, right? Length contraction. So let's cover that in a lengthier way, okay? Length contraction. So here you go. The way we explain length contraction is by considering two planets separated by a distance L and a spaceship moving at relativistic speed, right? At a relativistic speed v. Relativistic speed v, I would say something around greater than 20% the speed of the light, right? That's when we start to see some real changes, greater than 20% the speed of light, This spaceship is flying from the first planet to the second. For you who stayed behind, you measure the length of the strip as b, right? For you that stayed in the planet, you measure this length here. V L over delta t, the length of the trip. And that's going to be delta t equal to L divided by V. Okay, like that. L divided by V, let me put that like that. But let's not forget there is a relationship between proper time and the time in the spaceship, right? Okay, the time in the spaceship is related to the other time by this relationship here. And I call that, the length L prime divided by V. The length L prime that the other observer, right? In the moving observer measures. Okay. Another student coming. And now he go. Here's the length that the observer on Earth measures. So now we can pass this V to the other side. L prime. But let's not forget that V delta T is the proper length. And here you go, that's gonna be my proper length, L. And here we have a factor that's less than 1. Okay, and I'm gonna write that down. L prime Here we write it down as being L divided by gamma, like that. Okay, so the conclusion is, for you who stayed behind in planet A, which is at rest with respect to planet B, you measure the distance from A to B as being L. However, for an astronaut in the spaceship, he measured a distance L prime, which is less than L, by a factor of 1 divided by gamma. That's another consequence of the postulate of relativity. Here go A, B, C. Length contraction. Okay. An object moving past you at relativistic speeds is seem to be contracted. However, an astronaut inside this a spaceship, not an object, a spaceship, right? A spaceship moving past you at relativistic speed, it seemed to be contracted. However, an astronaut inside this spaceship measures contracted by a factor gamma. However, an astronaut inside this spaceship measures a length, L, factor gamma, L prime equal to L divided by gamma. Okay, that's another important and not what we have right now. Another way to illustrate that, let's see if I have let's see if I have it here. Yeah, unfortunately, let's see. Yeah, unfortunately, I don't have it here. Oh yeah, here you go. That's what it is. Okay, planet A and planet D, right? L is the length as measured by referential B. And let's not forget, he measured according to referential A, the amount of time that takes for this whole trip is going to be L divided by V. L divided by V. But according to referential B, no, it's going to take a shorter amount of time for him. Okay? And that can be accounted for his shorter amount of time only if this distance has been contracted. Okay? That's the explanation. Okay, that's another explanation. So let me get this illustration and place there. So, I'll put it right in here. Okay, here you go. Okay, so here you go, another explanation for that. You know, another way to explain. Let's put it here. I'm gonna put it after. Another way to explain length contraction is by considering the fact that an observer in A measure a length L equal to V, okay? Delta T in his proper referential. He also measures the amount of time that took the strip as being what? Delta T is equal to L over V. Since an observer in B will measure a smaller amount of time, delta T prime, okay, comma, something in his equation must give in, right? Delta T prime, and then I'm going to write that down. Here you go. Delta T prime would be L prime divided by V. So something in his equation must give in. What gives in? What gives in is not the velocity V, but the length L, which becomes L prime. Okay. Since, okay, delta T prime is less than delta T, comma, then L prime must be less than L. Like that. And that's the result of length contraction. Let's see what we have covered in the book. This one here. Okay, events and inertial frames of reference 28.1, postulates of special relativity. Let's put it here. Move it away. And sections of the book covered so far. Okay, 28.1 events and inertial differentials, frames of reference, right? Frames of reference or reference frames. (28.2) the postulates of relativity, of special relativity. 28.3 the relativity time dilation. That was time dilation. 28.4 Planck's contraction. What's going to come next is the relativistic momentum. 28.5 relativistic momentum. Whatever it's in both phase, it's has been covered. And we're gonna, the next one is gonna be relativist moment. Let's write down everything. Equivalence of mass and energy. And 28.7 relativistic addition of velocities. Okay. 150. So let's take our little break, right? But before we go into the break, let's take attendance. 13. Jacqueline Hernandez, are you there? I don't see Jacqueline. Oh yeah, Jacqueline is here, right? Thank you, Jacqueline. Sky here. I don't see Sky. Ashley. I don't see Ashley either. Corina. Hello, Corina, are you there? Okay, good, thank you. Next is Norberto. Norberto seems that he disappeared. Vanessa Mena is here, right? You're the first one to arrive. Thank you, Vanessa. Yorgo, is Yorgo here? I see Yorgo in the list here.
Yes, here.
Okay, thank you. Paul Zapata. Thank you. 5 students. Okay, good. So we have, let's take our break now. It's break from 8:50. See here. (9:52) right now. To 10:07. Okay. Any questions about that? Okay, so I see you in 15 minutes. Okay, I'm back here. And let's talk about the relativistic momentum now. And okay, recall that from physics 7 that the regular momentum or Newtonian momentum, right? Regular or Newtonian momentum is given by m times v. Okay, we also know from physics 6 that if the net force applied to the system is 0, we know that this quantity is conserved, right? That like that, you know, if you know, if net force equal to 0, that implies, right? That implies that initial momentum is equal to final momentum, right? And where does it come from? Well, it comes from Newton's second law. And I'm going to consider that a vectorial. Let's make it, you know, let's make it genetic enough. Not just a scalar quantity, but a vectorial quantity. And how do we know that? We know that from Newton's second law of motion, right? Which is mass times acceleration equal to 0. And let's do the math, right? The complete math here we go. Acceleration is what? Delta V over delta T. Right? And because momentum is mv, what you end up having here is final velocity minus initial velocity. Right, here you go. We can put m there at the top. M at the top here. mv is going to be my final momentum. Let's simplify the notation, right? P is final momentum with no subscript, just to simplify the notation. And mv naught is the initial momentum. Okay. One more step is going to be something like that, right? And finally, we have this final step here. P naught equal to Pf. So the whole idea of momentum, so the whole idea of momentum so let's see. So if we want right here to define a relativistic momentum, comma, we must also have a definition. We must have its definition to be conserved. In relativity as well. In order for that to happen, come on, momentum is defined in the following way. Relativistic momentum, right? Momentum is defined in the following way. Okay, if we still have MV. We still have MV here upstairs. Okay? But then we have to apply that gamma factor to the MV. And more specifically, I'm going to write that in terms like that. Okay? And this term here that you see, we call the relativistic mass. Okay? Okay, so this definition, this new definition of momentum ensures that it is conserved in both referentials A and B, where B is moving with respect to A and vice versa. Okay, so I'm going to repeat that definition. Go and emphasize that we have this gamma factor times MV. Okay. Okay, if we use, if we use this the above relation, right? If we use the above relation, we find the following: the numerical value of the relativistic moment measured with respect to referential A is still different from the numerical value measured referential B, just like we get in mechanics. Just like in mechanics, okay? Like in mechanics. However, for this specific formula, for this specific formula, for this specific relation, for the relativistic momentum, comma, it is conserved in both referentials A and B, okay? So, but don't forget for net force, right? If you use the above relation, we find the following. Whenever the net force applied to an object is 0. Okay, don't forget, we still have to have a net force equal to 0. So you're gonna put like that. We go. Initial relativistic momentum measured with respect to referential A. In other words, if net force is 0, right? Initial momentum with respect to referential A is going to be equal to final momentum with respect to referential A. And we also have the same for the referential B. Okay? We have the same for referential B. That's why we end up with this slightly different relation for the relativistic momentum. And here I'm going to point out that this one is the Newtonian, right? Newtonian momentum, Newtonian linear momentum. And I gotta put the vector as well. Here you go. Vector as well. Here too, right? Here's a vector as well. Although it's a relativistic momentum, it is still a vector. Like that. Now I'm going to repeat this formula here. This term I'm gonna put in boldface. This term that you see right here in boldface is usually referred as the relativistic mass, implied that the mass increase that moves faster and faster. Okay, as it gets closer and closer to the speed of the light, this term becomes zero, right? And this ratio that you see right here goes to infinity. Okay. So now we have another unexpected result of relativity. Okay, and what's that? You know, mass increases with velocity. Let's put it this way, relativistic mass increases with velocity. Whereas in mechanics, Newtonian mechanics, mass does not. Mass is not a function of the velocity, is not a function of velocity. So here you go. You know, and what about in other words? In other words, the length depends on the velocity, right? On the not the velocity, on the relative velocity. Let's make it clear, right? On the relative velocity, In other words, let's finish it here. Velocity. In other words, mass depends on the relative velocity. In other words, the period depends on the relative of velocity. The period of the other clock depends on the relative velocity. Similarly, whether an event is simultaneous or not, it depends on the relative velocity. That's why it's called theory of relativity. It has to do with relative velocity. Okay, in other words, oh, let's see. Nope. Let's put it here. In other words, if you see a particle flying by you, you measure a larger mass. However, someone else that's moving side by side this mass with a relative velocity of 0, with a 0 relative velocity, with 0 relative velocity, we'll measure a mass that coincides with the rest mass value. Okay. And now let's go back to our list of things, right? We did relativistic momentum. You go. And now we're going to do that, equivalence of mass and energy. The nice thing about the relativity is that many of the derivations, many of its derivations requires only algebra. Only algebra. Like the light clock, right? Light clock, time dilation, length contraction, and so on. But it's not for everything, okay? In the case of here of equivalence mass and energy, in the case of equivalence mass and energy, we need calculus. We need to use calculus. Okay? For this reason, we can only treat the, for this reason, I will just give you the final result with some steps along the way, okay? And how Einstein calculated this this equivalence of mass and energy, okay? Okay, going back to physics 6. Recall that the idea of work is central to energy. So much that work has units of energy or joules. J. For this reason, we start with work as well. And step by step is the following. Step by step without, without doing the math, the following. So here you go. It's possible. It's possible to derive the energy of a relativistic object by doing the following. First step, use the definition of network. Remember work kinetic energy theorem? Recall the work kinetic energy theorem. Here you go. Recall the work kinetic energy theorem. Right? Work done by the net force is the net force times the displacement. And we end up having this result here, final kinetic energy minus initial kinetic energy. Okay? But then we go ahead and apply the relation of momentum to the net force. Remember, net force is equal to delta P over delta T, right? What is delta P? The relativistic delta P. It is relativistic delta P. And we still have delta K. Okay, and then that's where we have to work out the math, the high-level math, calculus-based math, and that's where I'm going to skip doing that because this is not a calculus-based course, right? Numbering value. Yeah. Oh, yeah. Like that. We get that the relativistic energy is going to be given by the relativistic mass multiplied by c squared times that gamma factor. See where gamma shows up so frequently, right? The relativistic energy depends on the speed of the particle. And the closer you are to the speed of the light, the larger this energy becomes. The larger this energy becomes. Okay? So now, what if the mass? What if the mass is at rest? If the mass is at rest, it's not flying at the speed of relativistic speeds. This term here becomes 0, right? The gamma becomes equal to 1. And we end up with this Einstein's famous relation. Okay, I'll call that at speed equal to 0. I call that the rest energy, and we get mc squared. Okay, after some higher level derivations that involve differential calculus, that involves differential and integral calculus, we end up with the following formula. And now that was the equation that gave rise, that when scientists saw this relationship here, they start applying numerical values, and we can do that, right? Let's do that. Let's see, what would be the rest, what is the rest energy for a mass, for a 1 kilogram mass, right? What's the rest energy for a 1 kilogram mass? We can do this math. Let's do that. Okay, here is my I'm gonna do something else. Let's see. I'm gonna use my favorite software, Live Mass, here, because that gives me the numerical result right away in a more intuitive fashion. Here you go. So here you go. Rest energy is equal to mc squared. Okay, m for one kilogram. And C, you already know that's 300,000 300 million meters per second. Like that. 300,000 kilometers per second, which is 300 million meters per second. Notice this is a very large number, right? And let's see what we get for the rest energy. Here you go. And now we are going to square the C, expand. Yo, I'm going to simplify this result here. And what you see right in here is, in reality, the definition for joules. Predefine, user define, okay? Use define. Okay, like that. So let's see if we can figure out what this value is. Okay, let's see how much energy this thing is actually. It's 10 to the 16. Looks like a very large number, right? I'm going to copy and paste it there. Here you go. Now let's try. Now here you go. Let us try to make sense of this number. In other words, let us figure out how large it is. Okay. One way to do that is by comparing the average, is the average energy usage by a house. Okay. You know, look at your bill. Look at your electricity bill. And find out how much energy you spend on average. Okay? I can tell you right from the bat that an average house, I'm talking about an average house, right? Spends roughly, 400 kilowatt hour per month of energy, of electricity. Look at an average house. Let's see how many houses we can power with this energy. Notice that we have here this energy measured in joules, but here we have a different unit, is the kilowatt hour. So we have to change this kilowatt hour into joules to find out what 1 kilogram mass, right? What the energy of a 1 kilogram mass would be able to power. How many houses, right? How many houses, let's put it this way. How many houses would we be able to power in a given month with this amount of energy, right? This amount of energy. That's what you're doing here. Trying to make sense of this number. Now let's try to make sense of this large number. Let's try to make sense of this large number. In other words, how many houses can we power? In a given month with this amount of energy? Okay, and assume that an average house spends 400 kilowatt hour of energy per month. and then you can also look at that. You can also look at your electricity bill to find out how much energy you spend on average, right? But 400 kilowatt hour is a good one. It's a good number. So solution. Now I'm going to do that, here on my one house spends a house on average 400 kilowatt hour of electricity per month. Okay, which is how many joules? Well, let's figure it out. 400 kilowatt hour. It's not difficult to convert. Okay, kilo. I'm gonna put do like that. Kilowatt times hour. That's what kilowatt hour is all about. It's kilo times watts times hour. Okay, we already know that kilo is 1,000. We know that watts is joules per second, right? And we know that hour, I'm translating all of that into the SI units. 1 hour is 3,600 seconds. There you go. I will substitute that all up here, what? Bring it down here. Watts is going to be joules per second. Hour is going to be 3,600. Notice that 400 kilowatt hour is also a large number, right? Let's see. 1,000, 1, 2, 3 million, billion, 1 billion. 1 billion is 1.44 times 10 to the 9 joules. Okay, so 1.44 times 10 to the 9 joules. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. That's what 400 kilowatt hours is. It's still a large number, right? It's still a large number because it's 10 to the 9 joules. But we're talking about 10 to the 6 joules. Okay? So in order to find out how many homes we can power with the energy, with the rest energy of a 1 kilogram mass in a single month, all we have to do now is to divide E naught by 400 kilowatt hour. Watt hour. Okay, so here we go. I will replace it right here. I will replace this one. That's on the order of, let's see, 9, well, 1 million houses, 10 million houses, more or less. Okay, here you go. 6 million houses. 1, 2, 3. Let's see. 1, 2, 3, 1,000, 1, 2, 3. Actually, 62 million houses. 62 million houses should be, roughly the whole United States. Have you thought about that? If you have the United States have what, 300 million people living? Let's say 4 people per house. 300 million divided by 4, we get approximately 70 million houses in the United States alone. So this, if we were able to convert all the energy, all the rest energy in a mass of 1 kilogram, we would be able to power the United States for a whole month. all the houses in the United States for the whole month. Okay? And that's what we are getting here. That's impressive, right? Yeah. 1, 2, 3, 4, 5, 6, 7. Yeah. So going back, that's just so when scientists saw something like that, they were impressed, right? With the amount of rest energy in a kilogram mass, we would be able to power 62.5 million houses in a single month. In a single month. Let me get someone here. Here we go. Okay. 62 million, 62 million and a half houses is roughly the number of residences in the United States alone, Okay? And how did I get this number? Well, just divide by, how did I get this number? I just divided the US population, 300 million people, by 4, which is the size of a family, the size of a regular family. Is the size of a regular family. Okay. 300 million divided by 4 is 75 million houses, close enough to 62 million. Okay. So when scientists saw that, they start thinking about weapons. And that's what the movie about Oppenheimer is all about, right? Einstein derived this equation, he looked at this equation, and my goodness, right? We can build a weapon that's powerful enough to annihilate a city, a whole entire city. It has enough energy to level a city, but this energy also can be used for something else, can be used for some practical purposes, to power the houses, right? To power many residences. And that's why we are considering using nuclear energy, nuclear power plants. That's why we use nuclear power plants, because it stores a huge amount of energy. The only problem with nuclear power plants, million houses, I gotta put here, it's roughly. The only problem with nuclear power plants is how you're going to dispose the junk that's left over of this reaction, right? That's the problem with nuclear power plants. And did you get an idea of how much energy we can store just as a single kilogram, right? The rest energy. And when scientists look at this result, right, obtained by Einstein, they realized that we could tap into this energy to either power an entire country or create weapons of immense destructive power than the atom bomb and the hydrogen bomb. Then the atom or fission bomb and the hydrogen or H, or fusion. Another name for the H bomb is the fusion bomb. There is fission bomb and then there's fusion bomb. There are two different types of nuclear processes: fission energy and fusion, and energy produced by fusion of nuclei. Okay. In the case of nuclear fission, a single atom is split into two. Okay, that's what fission means: to break, to split. In the case of nuclear fusion, two not atoms, two nuclei, right? A single nucleus, a single atomic nucleus is split into two. In the case of nuclear fusion, two atomic nuclei are combined in a single one. Okay, 10:52 right now. And any questions about that? Let's take a look at the book. Let's see, book here. Relativist mass and energy. That's what we want here. Rest energy of an object, total energy of an object, exactly the same equation that I had. Rest energy, the energy equivalent of a golf ball. Okay, he calculated that, and how much did he get? Rest energy, solution. Let's see, let's read this problem here. This one on the green. If the rest energy of this ball were used to operate a 75-watt light bulb, right? How long would the bulb remain lit? Okay, so what did they get here? 1.7 million years just for a 70-watt light bulb. I did an equation I did a problem slightly different, right? I just want to know how many houses I would be able to power with a 1 kilogram rest energy. Go. And what about the kinetic energy? Let's talk about the kinetic energy too, right? That's very straightforward. Kinetic energy of an object the relativistic kinetic energy is given by given by the relativistic energy minus the relativistic rest energy, like that. And we can write that down as being MC squared over the square root, the gamma factor, right? 1 minus V squared over C squared. And then we write that down, MC squared. And we end up having this relation here. I'm going to put MC squared in evidence. 1 here, 1 here. Can we do better than that? Doesn't look like, right? We're gonna have minus here. Yeah, we cannot do much more than that. Oh yeah, there's one more thing that we can do. We can go ahead and get this guy here expanded in series. Okay, in Taylor series. Either this one here or this other one here. Okay, it's better if you expand this one here. It is possible, right, to come up with an approximation, and we call that the binomial approximation. I'm going to write here. Let me erase that because we're not going to use this one. Okay. This number here is always going to be less than 1 because the speed of a particle cannot exceed, of an object cannot exceed the speed of the light. Nobody has ever observed an object that travels a superluminal speed. Okay, and there is a nice approximation that we can come up with for this type of 1 plus a number, 1 minus or plus a number less than 0. Now can be written down as being as a series. Here you go. The power goes here. Okay, that's the first term. That's called the binomial approximation. This is a mathematical relation. And then the next term would be, you know, I'm going to emphasize that this term here has a power of 1. Okay, I'm emphasizing here. I don't have to do that, but I'm emphasizing. The next term is going to have a square value. And the other term would have a cube and a 4th power and so on. And then we have this term here that depends also on the power and something else. Okay. So using the first order approximation, the following result. We have to change it to an approximation sign, like that. I neglect everything else. And we end up having what? 1 plus half V squared over C squared. I didn't finish yet. Going back to my equation for kinetic energy, look what we're gonna get. Okay, I'm going to use an approximation here. I'm gonna copy and paste it here. And on the top of that, I'm going to replace that ratio with my approximation. Okay, And look what we are going to get. This one here cancels this other one. This one here cancels this other one here. Okay. And the c squared that we have here is going to cancel the c squared as well. Look how nice we get c squared. C squared. V squared. V squared. And then look what we're getting here. When we use Einstein's equation, Einstein's result for the kinetic energy, right? We get the relation that were taught to you in mechanics. So mechanics, Newtonian mechanics is just, what does it mean? Newtonian mechanics is just an approximation to Einstein's theory of special relativity. And that's exactly what is in your book as well. Okay, here you go. Then we have here this example, high-speed electron. What time is that? 11:02. Because, let's see, an electron of this mass accelerates from rest to a speed of close to the speed of the light in a particle accelerator. Determine their electron rest energy, total energy, and kinetic energy in millions of electron volts. Okay, so rest energy, just get the mass of the electron multiplied by c squared and 10 to minus 14 joules. Okay, if you were able to completely convert all the mass of electron in energy, that's how much energy you would get. In terms of electron volts, which is another unit of energy, we get this value here, half mega electron volts. Now, if the electron is flying at this relativistic speed, okay, the energy is gonna be, it's slightly more, 3 times more. 3 times, no, it's more, 30 times more. Okay, you multiply half by 30, we get around 15, which is close to 12, 16 mega electron volts. Okay. And here we have the total energy. If you subtract from the rest energy, you get the kinetic energy of the electron. Okay. Now look what the mistake that we incur if we use the Newtonian mechanics, right? Instead of getting the 15.7 mega electron volts, we get something that's far less. We get something that 10 times, 70 times less. But that's because the speed is very high. That's because the speed is very high, okay? We can even come up with a table here, a comparison table for speeds, okay, of the electron. The slower the electron speed is, the closer it's going to be to the kinetic energy, the regular kinetic energy in mechanics. Okay. Let's do that. Let's repeat this problem, not for this type of speed, but let's repeat that. Repeat example 9 in the book, right? Repeat example 9 in the book for V equal, 0.995, but 0.1 C, right? That's what they're going to do now. Going back here. Well, the rest energy is not going to change. Okay, this one doesn't change because it's the energy at V equal to 0, right? What's going to change is the total energy of the electron and the kinetic energy. That's what's going to change. So let's do that. And go E equal to 1 divided by 1 minus V square over C square. What else? Mass C square. And I'm going to use V equal to 0.1 C. I am going to expand, and then we go ahead. Let's see if I can get this. Calculate. Yeah, I calculated. And now I have to put C squared there. C is right here. Don't forget that I am doing here. Calculate, expand. Okay. Simplify. Okay. That's what I'm getting for. And now I have to change that to electron volts, right? Total energy, they're getting 10 to minus 12. Let's see here. What am I doing wrong? Oh, okay, I know what happened here. Gotta be careful with those things. Yeah, see here? I gotta put the mass of the electron here. This M here represents mass, and this other M here represents meters, right? Gotta watch out for those things. So mass of the electron is, let's substitute the mass of the electron first. 9.1 times 10 to minus 31. 9.1 times 10 to minus 31 kilograms. Okay, now we can put the C there, otherwise you're going to incur in that mistake. C. And now expand. Okay, now we have the right unit, right? Joules. Minus 14. It has to be less than what we got there in the book. Minus 14 is 2 orders of magnitude less than what we got in the book. It's slightly less than 2 orders of magnitude. And let's convert that to electron volts, right? Which is another unit. 1 EV. Oh gosh. 1 EV. Okay, now we got it. 1.6 times 10 to minus 19 joules. 1.6 times 10 to minus 19 joules. Oops. Joules. Okay. I'm going to change joules to electron volts. That's the energy I'm getting. I still didn't finish it. Let's expand. Yeah, 10 to 5 electron volts. How much do you get here? Yeah, a tenth of 0.5 mega electron volts. 0.5 mega electron volts. I'm getting 16 mega electron volts. Okay. And now we are going to subtract, right? The energy minus the rest energy of the electron. And I'm going to use the rest energy of the electron as being 0.5 times 10 to the 6 electron volts. 0.511 times 10 to the 6 electron volts. Let's see if we can get. Okay. Expand. Okay, I get a number greater than 0, right? Let's change it to joules. Let's change that to joules. 10 to minus 19 joules. And now let's use the kinetic energy for the Newtonian formula for the kinetic energy. And let's see what we get. Half mv squared, right? Half mv squared. Let's see if it's close enough or not. This one is m here. The velocity is 1/10 of the speed of the light. Here you go. Right in here. And we have to convert C as well. C is right here. Expand, and that's Newtonian. 10 to minus 16. Let's try to, we have to expand here first. Okay, now look at the result here. Here we're getting 10 to minus 16. Here we're also getting 10 to minus 16, right? That's joules. So there is still a difference, okay? There is still a difference, but the order of magnitude is the same, okay? The order of magnitude is the same. We are talking about a 20% difference. 1.5, 1.5 in 5, 1.5 is 30% difference, a 30% difference only. A 30% difference only, right? That's because the speed is 0.1 c. And 11:14 right now. Any questions? Let's have our break again. And going back here. For book, let's see, let me put the answers here, right? You go, Newtonian, not Newtonian, the relativistic formula states that the kinetic energy of the electron is, you go, that much. Using the Newtonian formulation, you know, KE equal to half mv squared. We get the following result. Okay, which is only 30% different. Okay, the slower an object moves, the closer the Newtonian formulas will be to the relativistic equations. Okay, so let's go to our break from with 11:16 right now to 11:31. Okay, so I'll see you in 15 minutes. Oh, sure. I'm back here. And now we finish. Let's take a look here. Equivalence of mass and energy. What I want to do is to do a relativistic addition of velocities as well, finish this chapter. That's this chapter here is not in the old notes, okay? At that time, I didn't have time to cover that addition of velocities, but I'm going to cover this time. This information. Okay. Transformation equations. Okay. Okay. Here you go. And that's the book here. The well, here they don't derive those equations, okay? Those relatives. Here in the book, they don't derive those equations. And that's because it also involves advanced calculus. But at least the formulas you should be able to use. You should know how to use, okay? So let's first talk about the relative velocities of different referentials, right? So in physics 6, right? We found that the relative velocity of a given point P can be given by, let me just remind you, and I'm gonna, how we get those velocities in physics 6. And then we can go for the relativity equation, which is kind of similar, but there are some important adjustments that needs to be made, okay? Oh no, not this one here. Relative velocity. What's going on here? Okay. Relative velocity. I want to show you the drawings too that I have. I'll get it. Relative velocity. Well, doesn't look like I have it here. Yeah, we don't have it here. Let's see, it's on the other one. Okay. Okay, here you go. That's the drawings that I do in physics 6. Okay, so here you go. Here we have two different referentials, A and B. Okay, and here we have a point P. Okay, referential B is moving with respect to referential A. That's the velocity here is moving away. Okay, and here are the vector positions of referential B with respect to A, referential the point P with respect to referential B, and the point P with respect to referential A. And the referential A with respect to point P is minus this one here, right? That's why I put in this direction. Here's the velocity. Let's write it down, okay? And I'm gonna put it aside. We need to refer to our results in mechanics so we can have a better idea. So you can, not a better idea, but we can better memorize the equations for relativity, okay? Okay, so consider given by, I'm gonna do the following. Here you go. Consider two referentials A and B, okay? referential B is moving with respect to referential A, and its velocity is written as V, B with respect to A, okay? Velocity of B with respect to A, that's what it means. Like that. And I'm going to simplify our drawing. Okay, so we go. So I'm gonna get my drawing and a simplified drawing and put that in my notes. See figure. Okay, that's the type of drawing that you want to remember. Referential B moving with respect referential A. In addition to these two referentials, we also have a point P. You also have a point P somewhere in the space, somewhere in the space, also moving with respect to the other two referentials. Okay, and here is going to be my now in the next drawing, I just added, all I did was to add point P to the figure. Okay, and this point P can be located using either the referential A, either referentials, right? A or B, A or B. Accordingly, we have the vector position of P with respect to A, comma, and the vector position of P with respect to B. And I can write that down according to my respect to A here. I'm going to write that down here. Vector position of P with respect to A and the vector position of P with respect to B, like that. On the top of that, and then I'm going to show you the vector position P with respect to A and vector positions of P. Interesting. With respect to B. Yeah. Okay. I will copy that and put in my drawing here. And let me show you also this drawing, so you know what I'm doing, right? Here you go. So what do we have here? First, we have the two referentials, A and B, right? Then what did I do? I added the point P to this referential. And in the next slide, I have the position of point P with respect to the other two referentials. A little bit displaced here. Oh my goodness, what's going on here? Huh. I don't know what's going on here. Let's see here. Oh, whoa. Ay. Here you go. I want to keep. Okay, I'm going to do the drawing from scratch. Here you go. P with respect, vector position of P with respect to A. And I'm going to put it in red color. I'm going to make it a little larger, right? And differential vector position of point P with respect to B. And I'm going to use this one here. The other one here with respect to B. Make sense, right? Why am I doing that? You're going to see why am I doing that. It's just to refresh your memory, right? How when we covered relative position and relative velocity. Okay, and this notation is very intuitive that I'm using. On the top of this two vectors, I also have this other vector that is what? Relative position of referential B, the origin of referential B, with respect position of referential B with respect to referential A. We have this other vector position as well. I need those three vectors to show you what I'm going to do. Let's flash it again. Here you go. One, play the movie again, right? Two referentials, point P, you know, right? I can even go a step further than that, right? I can, gosh. Huh, so odd. My goodness, this thing is all screwed up. Well, I'm not going to do that. I'd rather when I struggle with the same, delete the slide. Okay. So here you go. P, vector position of P with A and B, and vector position of B with respect to A. Okay. I don't need that anymore. I don't need that anymore. Okay. Now let's go back to this drawing here. Notice that the relative position of P with respect to A can be written down as position of B with A and position of P with B. Okay, you see that? This vector that you see here is the vectorial sum of those two. Okay, and I'm going to write that down in my notes. This point can be located using the differential, either differentials A or B. Okay, and I got also to copy the slides that I have here. I'm not gonna copy everything, otherwise my document is gonna become too large. According to the above figure, we have the following relations for the position vector of point P. Okay. Position vector of point P with respect to referential A is equal to, I'm gonna do this one first, and I have a reason to do that, right? Position vector of point P with respect to B plus position vector of referential B with respect to A. You see that? Why am I doing that? Well, because this notation is very intuitive. If you forget the proper order, all you have to remember is that the P comes first, right? And I'm gonna put that in different colors. And the P here comes first as well. The A comes last. I'm gonna put in a different color. And the A here also comes last. And whatever repeat, whatever is repeated here, doesn't show up in the left side of the equation. Okay, so this type of using this type of mathematical rule, and it is a mathematical rule. Now we can come up with all sorts of vectorial relations. We can say that position of P with respect to B is equal to position of P with respect to A plus position of A with respect to B. Okay, we can get something like that too. And if we have the point P as a referential as well, what we can do? We can have position of A with respect to B, position of A with respect to P, okay? Position of P with respect to B. We can have the same type of relation. All those three equations, they are the same. This one is gonna be, okay. And how does it relates to relativity? You're going to see in the next step, okay? In the next step, we are going, what you see above, is just it's just the equations for relative position. Okay? We have similar equations for the relative velocity. Okay? All we gotta do is to do delta R over delta T. And when we do delta R over delta T, we get the following relations. V of P with respect to A is V of P with respect to B plus V of B with respect to A. And we get the same thing for V of P with respect to B, V of P with respect to A, and V of A with respect to B, and and so on. Okay. We're going to concentrate on this equation here because in general we know the velocity of P with respect to A. Okay, we're going to concentrate on that. Let us concentrate on the second equation. Let's concentrate on the second equation. Okay. It happens. It happens that when we are dealing with relativity, the above equation changes slightly. What you see above is the vectorial. What you see above is the vectorial addition of velocity in mechanics, right? It happens that when we're dealing with relativity, the above equation changes slightly. Okay. You're still going to have the same values here at this point, but then you also have to make a correction, and this correction can be derived. And how is this correction going to be? Okay, this correction is going to be in the following way. This correction is going to depend on the speed of the light, by the way. And it's going to look just like that, okay? So the velocity of point P with respect to referential B is going to be the vectorial summation of the velocities, but it's going to be divided by this term. If this velocity here is much less than that, what do we get? Okay, if, VAB much less than C, if VAB and VPA much less than C, right? Then the above equation returns to the original one in mechanics. Or this term becomes negligible, right? And we have this approximation. Okay. Consequently, the relative velocity equation in mechanics is an approximation of the relativistic one. Okay. And then we can start looking at some examples. Okay, let's compare that with the book. We go. He put here in terms of. He didn't put that in terms of. Let's take a look at the notation, right? B B G G T T, right? I use point P, right? B B G G and T T, right? And then here is the correction term. Okay, it's the correction term. A B B CC. Okay, and we have here the velocity of the ball with respect to the truck. That's what this, okay? Velocity of the ball with respect to the truck. And that's, we also have velocity of the ball with respect to the ground. And velocity of the truck with respect to the ground. So when you do something like that in mechanics, the velocity that this guy is going to measure for the ball is going to be the velocity of the truck or the velocity of the ball, right? 15 plus 8 is going to be 23. In relativity, it's not quite that. If we're dealing with relativistic speeds, the velocities do not sum like that in a straightforward way. It has to have that relative term, right? That correction term. Okay, so let's do an example. Okay, so consider example, right? I'm going to repeat that for the ball. Example, consider VP with respect to A equal to, let's say, 8 meters per second, right? Now let's put 15 meters per second. Okay. I'm going to copy the example that we have in the book. A is going to be my ground. Okay, V of A equal to, let's say, 8 meters per second, right? Find VP of B and VP of B in two different ways. One, using equations in mechanics, and B, using the equation, the relativistic equation. No, not the equation in mechanics. Okay, what we get? Solution. Okay, so here we go. Item A. This one right in here. I'm gonna put here equality because it's mechanics. Here you're gonna have 15 meters per second. And here we get 8 meters per second. When you sum that, you get 23 meters per second. Okay. In this case, A is the truck. Okay. In this case, A is the truck. In this case, A is the truck. B is the ground differential. And P is the ball that is being propelled. Now let's solve the same thing using relativity. The formula is slightly different, right? You already know that what goes upstairs is going to be 23 meters per second. And don't forget, this thing is, strictly speaking, we have here a vector, right? The ball is being propelled along the positive direction. Positive direction of the x-axis. And so I gotta write that down in terms of the vector. And here upstairs, we already know that's gonna be something like that. Velocity, speed of the referential A with respect to B is gonna be 8 meters per second. The speed of the ball with respect to referential A is going to be 15 meters per second. And now let's do this math, right? 8 times 15 divided by c squared. How much is that? It's a very small number, right? 8 times 15 divided by 300 million, 123 squared. What do you get? You get a number that's almost zero, right? 1.33 times 10 minus 15. See that? This. I want to write that down here. Meters per second cancel out with the meter per second that goes in C, right? Okay, and that's gonna be, it's so small that's not gonna make any difference whatsoever. 10 to minus 15, like that. Your equipment is not gonna be able to measure this thing at all. It's gonna be approximately 23 meters per second. Right? Now we're gonna change the problem. Now we'll change the problem. The values, the numeric values, we'll change the numeric values of the problem. Instead of using those small speeds, we're going to start using relativistic speeds, right? Instead of 15 meters per second, let's say 0.8, 80% the velocity of the light. And instead of 8 meters per second, let's see 0.5 C. Okay. Here can be a planet B. Here can be a spaceship A. And here can be a missile that I'm propelling from my spaceship. Okay. So what we end up getting here. Okay. What we end up getting here. Oh, so we're already run out of time, right? Oh man, just noticed that. Okay, let's stop here. Sorry, folks. I was so concentrated here on solving this problem, but we continue doing that next time. Okay, and nobody told me that, but let's stop here, and I'll see you Wednesday. That's gonna be our exam. Okay. So
Wednesday is gonna be the exam, right, Professor?
what? What's the
This
question?
Wednesday, right?
Yeah, the day after tomorrow. The day after tomorrow, right in here. Here you go. 15th of May, exam 3. Chapters 22 through 26, labs 3, 4, 5, and 6. 8:50 a.m. to 10:50 a.m. Okay? On Canvas. Okay, so I see you on Wednesday again.